Welcome back to Emoji Economics. My name is Odwale Godwin. What shall we be talking about today? We shall be talking about how to solve a question on the CES production function. In the previous class, we learned about introduction to the CES production function. We were able to calculate the marginal product of capital as well as the marginal product of labor. So in this particular video, we shall be applying many of the things we learned in that video in this particular one to solving a question. So we have a question, a CES production function, which is Q equals 75 into bracket 0.3k raised power minus 0.4 plus open the bracket 1 minus 0.3 close the bracket n raised power minus 0.4, then we close the bracket, all of that raised power minus 1 over 0.4. So if you recall, remember that 75 is going to be the efficiency parameter, 0.3 is the share of capital in output, 1 minus 0.3 is the share of labor in output, then minus 0.4 is the parameter that is used to estimate the elasticity of substitution. Then 1 here, 1 is telling us the returns to scale that is being exhibited by this production function. Okay, and since all of this we have minus 0.4 minus, remember that in the previous class this was v over rho. Okay, and here since rho is this and this negative, it simply means rho here is as well negative. Okay, and it's the negativity of the rho here that made the entire fraction to become minus 1 over 0.4. So what we just do is to take the absolute value, which is 1, we take 1, and 1 simply means there is constant returns to scale in this production function. So we have that, and we have a constraint. Okay, we have a constraint, a budget constraint, which is 120 equals 4 units of capital plus 3 units of labor. So what are we to do? We have to find the output maximizing quantity of labor and capital and the production function above, subject to the budget constraint, and B, we have to calculate the output. Good. Now, how do we solve that? So you guys really need to pay attention. You really need to pay attention. Okay, so Q equals 75 into brackets. I kind of simplified this. Okay, so this is now going to be Q equals 75 into bracket 0.3k raised by minus 0.4, all of that. Then 1 minus 0.3 is as well 0.7, so 0.7L. Okay, then we close the O bracket, then minus 1 divided by 0.4 is simply minus 2.5. So that's equation 1. Then we change this to 120 minus 4k minus 3l equals 0. It's just the same thing. All we just did there was to make the equation equal to 0. Okay, so this is plus 4k, it comes here, it becomes minus 4k. This plus 3l, it comes here, it becomes minus 3l, and all of that equals 0. So the next thing we have to do here, which is where the real work starts to begin, is which is where the real work starts, is where we set up the Lagrangian function. So that simply means we are going to be introducing a new parameter which is called the lambda. Okay, we've spoken about lambda before when we were talking about the Cobb-Douglas production function, and we're able to see what it does. So if you don't know about that, if this is your very first video that you're seeing, you have to search our YouTube channel and just look for a video on the proof of lambda. Okay, it's under producer equilibrium, so the proof of lambda, you're going to see that where an entire video was devoted into proving what this actually says. Now Q equals 75 into bracket 0.3 k per everything that we have here. Now plus lambda into bracket the budget constraints. Now the budget constraint that was equal to 0. Okay, so we bring it back here. Now what do we start to do? So we find the marginal product of capital, which is the differentiation of the output with respect to capital. Okay, so what happens? Remember that from the previous class, this becomes minus 2.5, okay, times 75. All right, so that's why we have minus 2.5 here, multiplied by 75. We leave everything that's inside this bracket the way it is, so which is this, but then the power is going to be minus 1, so minus 2.5 minus 1. Okay, minus 2.5 minus 1 is simply what? Minus 3.5. Then that's not all. Multiplied by, we then differentiate what is inside this function, what is inside this bracket rather, with respect to k. Okay, and that is what gives us minus 0.4. We come here. Okay, so minus 0.4 multiplied by 0.3. Then k raised to power minus 0.4 minus 1 is going to give us minus 1.4. Okay, so we just have minus 1.4 and then we close the brackets. So all of that's not the end. Remember that we have an addition of this bracket. So we differentiate this bracket as well with respect to capital. So this is 4k. By the time we differentiate this, it's going to become just 4. But 4 will be multiplied by this lambda. Okay, so we have 4 lambda. Okay, so minus 4 lambda. So that is the way that goes. I believe you understand that. All right. So let's do it again. K equals all of this. So how do we differentiate with respect to k? It becomes minus 2.5 multiplied by 75 minus 2.5 multiplied by 75 into brackets everything that is here. We write it out. All right. So that is what's written out here. Then the power is going to be minus 2.5 minus 1. Okay, so that's going to give us minus 3.5. Then we multiply that by differentiating with respect to capital what is inside this bracket. Okay, and that's simply minus 0.4 multiplied by 0.3, then k raised to power minus 0.4 minus 1. So minus 0.4 minus 1 is minus 1.4. We close the entire bracket. Then we have this part, okay, and then we have capital inside as well. So when we differentiate that, we have the k here is going to give us a minus 4, okay, a minus 4. So a minus 4 times lambda. Remember that lambda is outside the bracket, so lambda belongs to every one of them. So minus 4 times lambda is going to give us minus 4 lambda. So upon further simplification, minus 2.5 times 75 is going to give us minus 187.5. You can just point that to your calculator to verify. Then into brackets, everything that's inside there, raised by minus 3.5 multiplied by this. So minus 0.4 times 0.3, that's going to give us minus 0.12, and q raised by minus 1.4 minus 4 lambda. Okay, so what we just have to do is to multiply this by this bracket. Multiply this bracket by this bracket. We can multiply this, but of course we can multiply this by there was going to be too cumbersome and rather unnecessary. So we just leave that the way it is, simply because the power here is 1 and the power here is minus 3.5. So we don't really need to do that. So minus 187.5 multiplied by minus 0.12 will give us 22.5. Then k raised to minus 1.4. Alright, into brackets everything that is there raised by this power minus 4 lambda. So that's equation 4. Good. So we are done. That's going to give us the marginal product of capitals function. Okay, so function is not a definite answer. So how do we get the marginal product of label? We do the same thing, which is the Q the L equals minus 2.5, okay, times 75. So which is what we've done here, minus 2.5 times 75. You write out everything that's inside that bracket again, raised per minus 3.5 times, then we differentiate what is inside. Okay, we differentiate what is inside with respect to label. Okay, so this is it. This is the initial function with respect to label. So that becomes, okay, minus 0.4 times 0.7L raised per minus 0.4 minus 1. Okay, and that's going to give us minus 0.4 times 0.7L raised per minus 1.4. So that is exactly what we are having here. Minus, what is it? Okay, times 0.4 into brackets 0 times minus 0.4 into bracket 0.7, close the bracket, n raised to minus 1.4 minus, we are left with one thing in the Lagrangian function here. So we differentiate with respect to, what we are differentiating now is the Lagrangian function. So we differentiate with respect to label. So this becomes minus 3. Okay, we have label here L. So this becomes, the L here becomes minus 3. Minus 3 times lambda. Lambda belongs to each and every one of them. Will give us minus 3 lambda. So minus 3 lambda. So we simplify again. Okay, this multiplied by this is minus 187.5 into brackets everything here times, we simplify this as well, minus 0.4 times 0.7 is equal to minus 0.28 L raised to minus 1.4. Okay, then minus 3 lambda. So we can still simplify this. So all we just have to do is multiply this by this. Okay, the power is raised to 1, the power is raised to 1, so that makes it easier to multiply. So this multiplied by this, minus 187.5 times 0.28 gives us 52.5. Then L that is here, L raised to minus 1.4 into brackets everything that is here to minus 3.5, then minus 3 lambda. That gives us equation 5. Okay, and then decode the lambda. So when we do decode the lambda disappears and we are left with all of this. Okay, lambda becomes 1 and we are left with, because this is simply 120 lambda minus 4k lambda minus 3l lambda. Alright, if we try to expand the brackets. So when we do decode the lambda now, lambda disappears with each and every one of them, and we have 120 minus 4k minus 3l at the end of the day. So that gives us equation 6. Good. So we set equation 4, 5, 6 equal to 0. So when we do that, This is equation 4. So by the time z is equal to 0, we have everything again minus 4 lambda equals 0. Okay, and all of that will give us all of this equal to 4 lambda. So that's just what we just have to do is to make sure 4 lambda jumps place equal to sign, and then it becomes a 4 lambda. So that's what there is to that. And this is equation 5. When we set it equal to 0, we repeat the whole thing. Okay, minus 3 lambda. Let me write the minus variable. Okay, minus 3 lambda equals 0. Okay, at the end of the day, we repeat the whole thing again, then equals to 3 lambda, and that gives us equation 8. Now, when we make equation 6 equal to 0, so we have 120 minus everything equal to 0, and then this becomes 120 equals 4k plus 3l. So which is just simple mathematics, and that gives us equation 9. Okay, so from there, what we just have to do is to divide equation 8 by equation 7. Now, equation 8 is what we have here by equation 7. You could decide to divide equation 7 by 8, but there's a reason why I just did 8 by 7. Okay, there's something I'm trying to drive at. So we just have all of this. Okay, this is equation 8, and this is equation 7. Okay, equals 3 lambda equals 4 lambda. Alright, so lambda cancels lambda. Alright, so what do we have? We are left with all of this. So remember that this 52.5 whatever is the MPL. Okay, MPL, and 22.5k. Where did you get that? But that was when we did DQ, which is MPK. So remember that 3 is the price of labor. 3 is the price of labor. 4 is the price of capital. Okay, so this is simply MPL by MPK equals PL over PK. Okay, which is the condition that needs to hold for a producer to optimize its output. Okay, and input use. So that is where the ISO cost is just potential to the ISO path. We've talked about that in one of our previous videos. All right. So what we just do here is 52.5 divided by 20.5. That gives us 2.33. All of this cancels all of this. So the complexity is out. Okay, so because they're the same. So 2.33 L raised by minus 1.4 divided by, we are left with K raised by minus 1.4. 3 divided by 4 is 0.75. So I think you are going to give a sign of relief now, because you are not dealing with complex things anymore. Okay, so 2.33 L raised by minus 1.4 is equal to just cross multiply 0.75 K raised by minus 1.4. Okay, we want to make L stand alone, so all we just have to do is to divide through by 2.33. So by the time we divide through by 2.33, there's nothing left here beside L, so we have L raised by minus 1.4 equals 0.75 divided by 2.33. Okay, and that gives us 0.32, then K raised by minus 1.4. But then it's only L that we need, so what do we have to do again? What we just have to do is to multiply the powers by minus 1 over 1.4. Multiply the power by minus 1 over 1.4. So L raised by minus 1.4 multiplied by minus 1 over 1.4 equals 0.32 is raised by 1, of course. So we just multiply that 1 times minus 1 over 1.4. Then K raised by minus 1.4, we multiply that by minus 1 over 1.4. Okay, at the end of the day, we discover that this cancels this. So we are left with just L. Minus cancels minus, 1.4 cancels 1.4. So we are left with L. Okay, equals 0.32. 1 times minus 1 over 1.4 is simply minus 1 over 1.4. So L is equal to 0.32 raised by minus 1 over 1.4. And K raised by all of this, minus cancels minus, 1.4 cancels 1.4. So we are left with 1. Okay, so and that's it. That gives us a K. So L equals 0.32 raised by minus 1 over 1.4, then K. Alright, so minus 1 over 1.4, when we further simplify that, it's going to give us minus 0.71. So that is L equals 0.32 raised by minus 0.71 K. Okay, and L, of course, becomes 0.32 raised by minus 0.71 is 2.25. So approximately 2.25, then K. Alright, so if you used minus 1 over 1.4 directly, instead of converting it to decimal first, you are going to be having a 2.26 approximately. So that's just problems with decimals. Alright, so that gives us equation 10. So what we just have to do here is to substitute equation 10 in equation 9. So where is equation 9? This is equation 9. Okay, so now that we can express L in terms of K, so let's just substitute that into equation 9. And that is 120 equals 4K standing alone plus 3 into bracket. L is now 2.25k. So we just open the bracket, 2.25k, then close the bracket. So 120 equals 4k plus 6.75k, 6.75k. So 4k plus 6.75k is going to give us a 10.75k, and 120 divided by 10.75k is going to give us something. So what have we got here? 10.75k equals 120, and k equals 120 divided by 10.75, and that's going to give us 11.16 approximately. So we substitute k equals 11.16 into equation 10. So what is equation 10? Here it is. So where L equals 2.25k. So L now equals 2.25 into bracket 11.16. We close the bracket. We multiply this by this. L equals 25.11. So that means the optimizing quantity of k and L respectively is 11.16 and 25.11. Okay, question B says calculate the output. So we have calculate the optimizing output at this particular point. So Q equals 75 into bracket 0.3k. You know, the function of quantity when we began. Okay, Q equals 75 into all of this, then minus 2.5. Okay, minus 2.5 because minus 1 over 0.4 is minus 2.5. So we just substitute the value of k and L that we've obtained now into this. So Q equals 75 into bracket 0.3 open bracket 0.38 k equals 75 into bracket 0.3 into bracket 11.16 which power close the bracket which power minus 0.4 plus 0.7 into bracket 25.11 close the bracket which power minus 0.4, then everything which power minus 2.5. So Q equals 75 into bracket 0.3 into bracket this which power this is 0.38. I'm used to using two decimal places for consistency. That doesn't mean it's going to be very, very accurate, but that's a good problem with decimals anyway. Plus 0.7 into bracket, this raised by this is 0.28. Close the bracket, then 2 raised by minus 2.5. So Q now is 75, open this times this is going to give us 0.11, plus 0.7 times this is going to give us 0.20. Everything is by minus 2.5. Minus 2.5. Okay, so Q equals 75 into bracket, this plus this is 0.31. Okay, everything is per minus 2.5. And Q equals 75 into bracket, this is per minus 2.5 is 18.69. 18.69. Okay, 75 multiplied by 18.69 is approximately 1401.75. So this is the optimizing quantity. Okay, this is the optimizing quantity. So we are done with the question. K is 11.16, L is 25.11, and the quantity at which this process is going to optimize the use of its inputs is 1401.75, provided that is the constraint 120 cos 4k plus 3L. So that is that about that. Thank you very much for watching this video. If you have any questions, leave them in the comment section, share it with your friends, subscribe to my channel for more of our videos. See you next time.